Today, we will explore the Newsvendor model, a strategic tool for making optimal inventory decisions under uncertain demand conditions. In our exploration of the Newsvendor model, we will focus on its theoretical analysis, which operates under a single order, production, or replenishment opportunity. It presents a complex challenge due to the inherent uncertainty in demand. This uncertainty gives rise to a too much, too little problem. On one hand, if the demand exceeds the order quantity, we face lost sales. On the other hand, if the demand falls short of the order quantity, we end up with leftover inventory. Both scenarios come with their respective costs and risks. And our task is to navigate this balance to optimize the outcomes. To effectively implement the Newsvendor model, we follow several key steps. First, generate a demand model. The first step involves determining a distribution function that measures the range of possible demand outcomes. This could be a normal distribution function or any other function that aligns well with your specific scenario. Second, gather economic inputs. Next, we need to gather the crucial economic variables such as the selling price, the production or procurement cost, and the salvage value of inventory. This element will largely determine the cost and revenues associated with different demand outcomes. Third, define an objective. We must define our goal. This could be to maximize the expected profit or to satisfy a specific in-stock probability. Our objective will guide our decision on the order quantity. Fourth, determine the order quantity. Finally, based on the previous steps, we choose the order quantity that best aligns with our defined objective. By following these steps, we can make informed decisions that best balance the cost and benefit associated with uncertain demand. Let's examine a practical implementation of the Newsvendor model, focusing on the case of hammer and their three-halves swimming suit. Hammer, in its planning phase, generates a forecast for demand and submits an order to TEC company at the beginning of November. Following this, Hammer received the order from TEC at the end of January, effectively marking the beginning of the selling season. This season lasts from February until August. It is important to note that any leftover units at the end of the selling season in August are discounted. This fact underscores the need to have an accurate forecast and order quantity to minimize losses from discounts. Marketing forecast for sales stands at 3,192 units. Our challenge is to utilize the Newsvendor model to make an optimal decision on the order quantity, balancing the risk of unsold discounted inventory with the risk of missed sales opportunities due to stock outs. We will be taking into account factors such as production or procurement cost, selling price, and the salvage's value of discounted inventory. As we further analyze Hammer's 3/2 swimming suit case, let's focus on its economics and aim to identify the optimal order quantity. The demand model follows a normal distribution with a mean of 3,192 units and a standard deviation of 1,181 units. The selling price for each suit is $190, while the procurement cost from the supplier is $110 per suit. At the end of the season, any leftover units are discounted and sold for $90, which we refer to as the salvage value. To discover the optimal order quantity, we must consider both the cost and potential profit. In this case, we apply the Newsvendor model, which allows us to weigh the cost of having leftover inventory against the lost sales opportunity cost when demand exceeds supply. As we move forward with determining the optimal order quantity for the Hammer 3/2 swimming suit, we must account for two key elements: overage cost and underage cost. Overage cost, or CO, represents the financial consequences of ordering one more unit than what would have been ordered if the demand was known. Essentially, this is the cost you incur when you have leftover inventory due to overordering. It is calculated as the difference between the cost and the salvage value. For the Hammer 3/2, we calculate CO as $110 cost minus $90 salvage value, which equals $20. On the other hand, underage cost, or CU, refers to the financial consequence of ordering one fewer unit than what would have been ordered if the demand was known. This is essentially the opportunity cost you incur when you lose sales because of underordering. We calculate CU as the difference between the selling price and the cost. For the Hammer 3/2, we calculate CU as $190 selling price minus $110 cost, which equals $80. Balancing the risk and benefit of ordering an additional unit is a critical aspect of inventory management. By ordering one more unit, we increase the possibility of overage. The expected loss on the Qth unit is the overage cost, CO, multiplied by the distribution function of demand, FQ, which represents the possibility that the demand will be less than or equal to Q. On the flip side, ordering an additional unit reduces the chance of underage, resulting in a gain. The expected gain on the Qth unit is the underage cost, CU, multiplied by the complement of the distribution function of demand, 1 minus FQ. As we increase the order quantity, the expected gain from each additional unit decreases, while the expected loss from each additional unit increases. It's important to note that the expected loss or gain on the qth unit is determined by the cost associated with overage and underage, as well as the distribution function of demand. So, where does this leave us regarding the optimal order quantity? The optimal order quantity is where the expected gain and the expected loss are balanced at the intersection point of the graph. To maximize expected profit, we need to find the order quantity, Q, such that the expected loss on the qth unit equals the expected gain on the qth unit. This is achieved when CO times FQ equals CU times 1 minus FQ. By rearranging these terms, we derive the critical ratio. FQ equals CU divided by CO plus CU. The critical ratio represents the probability that we can satisfy all demand. That is, demand is Q or lower. In essence, to maximize profit, we should choose an order quantity Q that aligns with this critical ratio. In the case of hammer 3/2, we can compute the critical ratio as follows. Cu over Co plus Cu equals 80 divided by 20 plus 80 equals 0.8. So our target is to set the order quantity such that there's an 80% probability that all demand is met. This is the optimal order quantity in terms of maximizing profit and minimizing potential loss. Continuing on from where we left off, let's talk about what happens once we have determined the critical ratio. In our hammer 3/2 case, as we established, the critical ratio is 0.8. To identify the order quantity that corresponds to this critical ratio, we turn to the standard normal distribution function table. This is a tool that provides us with the Z statistic, a measure that corresponds to our desired probability or critical ratio. In cases where the critical ratio falls between two values in the table, we employ what's known as the round-up rule, choosing the greater Z statistic. In the case of hammer 3/2, we choose Z equals 0.85. Armed with this Z statistic, we can now convert this into an order quantity. The order quantity Q can be calculated as follows. Q equals mu plus Z times sigma. Here, mu represents the mean of our demand distribution, and sigma signifies the standard deviation. Substituting our values for the hammer 3/2 case, we get Q equals 3,192 plus 0.85 times 1,181. This gives us an order quantity of approximately 4,196. In conclusion, by strategically determining our order quantity based on our critical ratio and the round-up rule, we can optimize our expected profit under conditions of uncertain demand. Now, we turn our attention towards a crucial component in the Newsvendor model, the in-stock probability. In essence, this represents the probability of satisfying all customer demand. Let's consider an example where the order quantity Q is 3,000 units. In this case, for all demands to be satisfied, demand must be 3,000 units or fewer. So, where does the distribution function come into play? It provides us with the probability that demand is Q unit or smaller, essentially giving us the in-stock probability. Therefore, in our example, the in-stock probability is FQ, which also equals FZ. It's the probability that we have enough stock to meet demand completely. Let's now evaluate the in-stock probability for a specific scenario where the order quantity is set at Q equals 3,000 units. To determine the probability, we need to evaluate the corresponding Z statistic for this order quantity. By referring to the standard normal distribution function table, we can find the value of Fz. In this case, the Z statistic for Q equals 3,000 is negative 0.16, which we can then look up in the table. Upon doing so, we find that F in terms of negative 0.16 equals 0.4364. But what does this mean for our in-stock probability? Well, with an order quantity of 3,000 units, we can expect a 43.64% chance of satisfying all customer demand. This probability provides us with valuable insights into the likelihood of meeting customer needs and avoiding any shortages. By considering the in-stock probability, we can make more informed decisions regarding our inventory levels and ensure a higher level of customer satisfaction. It is a crucial metric that helps us strike the right balance between meeting demand and optimizing our business operations. We now delve into the concept of determining the order quantity to maintain a minimum in-stock probability. For the Hammer 3/2 product, we aim to minimize leftover inventory while maintaining a minimum in-stock probability of 99%. To achieve this, we follow a two-step process. In step 1, we determine the appropriate Z statistic from the standard normal distribution function table that corresponds to our desired in-stock probability. By comparing the values, we choose z equals 2.33 to meet our constraint. Moving to step 2, we convert this z statistic into an order quantity based on the actual demand distribution. Using the formula Q equals mu plus z times sigma, with a mean demand of 3,192 units and a standard deviation of 1,181 units. We calculate an optimal order quantity of 5,944 units.